Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of stellar evolution, and we're going to concentrate our efforts on understanding how intermediate mass stars go from the process of leaving the main sequence to the process of ultimately dying, or stop when they stop being stars. So let's go ahead and get started. Now, in a previous video, we saw how there is a couple of ways to look at this process, and the best way to do it is to sort of slice open the star and to see what's happening deep down inside. Let me remind you that intermediate mass stars are stars that are greater than half the mass of our Sun, and they're less than 8 times the mass of our Sun. So an intermediate mass star is actually what our Sun is, since our Sun, by definition, is a one solar mass star. If we slice open the star, you'll notice that deep down inside, if you recall from the last video, we have the core. This is where the nuclear generation of energy is happening. This is essentially where the hydrogen is becoming helium inside of the star, and through the process of hydrogen becoming helium, we have energy coming out. And surrounding that, we have the envelope of the star, which is mostly hydrogen, but remember, the envelope is not hot enough, and there's not enough pressure to make that hydrogen do anything other than just essentially sit there. So it's hot hydrogen, but it's not fusing. Now, by the end of its main sequence life, if you recall, every single star has converted its core from hydrogen into helium. And once the core becomes helium, the problem with helium is that the temperature needed for helium to fuse is a temperature that is 100 million kelvins. And an intermediate mass star spends its entire lifetime having a temperature at the core that is far below that 100 million Kelvin requirement. So what happens is the helium sits there, it is not hot enough to fuse, the core collapses and shrinks, getting hotter, and as the core gets hotter, the envelope expands. Now, this is the same set of slides. In fact, I'm recycling the same 3 pictures that a low mass star will also do. Remember that all stars, regardless of their mass, will suffer the same fate. It's how they deal with that and whether or not they can overcome that problem. Now, the main difference for an intermediate mass star is the time of this essentially how long it takes to go from one to the next to the next. Remember that there's a relationship that says the mass of the star determines how quickly it goes through its evolutionary sequence. So low mass stars take the longest amount of time to get to the point where they develop a helium core. Intermediate mass stars take a shorter amount of time. So for the Sun, for instance, the Sun will go from the beginning of its main sequence existence to the end of its main sequence existence, and it'll take about 9 or maybe 9.5 billion years to do that. And then eventually it leaves the main sequence. So an intermediate mass star does not take as long to go through all of its fuel because of its mass. Now, the main difference also is that where an intermediate mass star has the ability to go beyond the problems that a low mass star could not. If you recall, we talked in the last video how low mass stars never get the helium to fuse. And so they end their existence by failing at getting the helium fusion to start at the core. The difference for an intermediate mass star is reaching that 100 million Kelvin minimum temperature is possible. And so inside of a star that's an intermediate mass star, the helium fusion will begin. The correct temperature has been met. The energy starts to pour out of the star, and we have hydrostatic equilibrium reestablished. Energy flowing out will stop the collapse of gravity. So you notice all the arrows have stopped. The core gets no smaller. It has shrunk to the point where it's now hot enough. And if the core stops shrinking, the envelope will stop growing. And by this point, the star is a red giant star. And I'll tell you more about that in just a minute. Now, let me remind you of a couple things. So here's now a diagram based on what we started to talk about in the last video. The proton-proton cycle, where hydrogen fuses to become helium, requires a minimum of about 2 million kelvins to be able to have the right temperature to force all of these protons to come together and fuse. And the triple alpha process is one where 3 helium nuclei will fuse together, and in the process of fusion will become a carbon nucleus. But the temperature needed for this is 100 million kelvins. Now the sun can do this. The sun will have the ability to have a core shrink small enough to reach this minimum temperature to get the helium to fuse into carbon. And when doing this, we reestablish the energy that flows out. Essentially the nuclear engine of the sun, or any intermediate mass star, is restarted and the star continues along its evolutionary path. But by this point, the sun will have bloated its outer envelope, essentially growing the outer envelope to a much, much bigger size than it is today. And the sun will become what we call a red giant star. Now here's an artist's impression of what the sun will look like in the future, and it takes a few seconds to realize what this picture is trying to show. For instance, this little tiny yellow dot way down here next to this is the current size of the sun today. So the box is actually bigger to show you what is almost impossible to see down here. So here is the size of the sun today. When the sun shrinks its core, making the core hotter, and grows the envelope as a result of this, the sun will grow to become this big. So look at the difference between the sun of today versus the sun of the future. So when we say red giant, we really mean that. It'll be a giant compared to what it used to be, and the surface of the star cools because of its enormous size, and it becomes redder in color. Now notice some of the numbers here. It says that the sun as a main sequence star has a diameter of 0.01 astronomical units. Right now the sun is about 1 million miles across. But the sun of the future is going to grow to have a diameter of 2 astronomical units. Remember that the AU is the average distance between the Earth and the sun. Now, if that's the diameter, the radius is 1 astronomical unit. And so if you think about it, what that means is in the future, the sun is going to grow its envelope until the sun itself will be as big as the Earth's orbit around the sun. So our sun of the future will grow big enough to swallow up Mercury, swallow up Venus, and then reach the size of the Earth's orbit. So imagine the sun being as big as the orbit of the Earth. It will be truly a red giant star. And again, this is something that'll happen in about 5 billion years. Now, if we could look deep down inside of the sun at this point, the envelope has expanded. We have a red giant star. But what we have is a core that is becoming more and more carbon. Remember, the process of helium fusion produces carbon nuclei. So the core of the sun will become more and more carbon. A little bit of oxygen comes from the process as well. Surrounding the core, we have a shell of hydrogen fusion that is continuing to turn hydrogen into helium. So we actually get 3 layers. You get a carbon core, you get a shell of helium, and you get a shell of hydrogen that is fusing to become the helium, and then the helium, of course, is becoming the carbon. Now, at this point, this will be where our sun will reach a crisis that it will not be able to overcome. And let me show you why. If we go back to this, remember that deep down inside of the sun in the future, or any intermediate mass star, what's going to happen is you're going to end up with an accumulation of carbon nuclei. Now, carbon will fuse into another element. The process of nucleosynthesis is possible for carbon. Carbon can fuse into another element on the periodic table. The problem is carbon has 6 protons, each positively charged, and so it is also a very heavy nucleus. So the minimum temperature for carbon to fuse with other carbon nuclei is 600 million kelvins, 600 million kelvins, 6 times hotter than what is necessary for helium to fuse. So the problem is the sun is going to have to make its core temperature hot enough to get the carbon to fuse. And to be able to do that, the core is going to have to shrink to get to that point where it becomes hot enough to get that to happen. So the sun at 100 million kelvins is not hot enough to get the to get the carbon to become the next element. It was hot enough for helium to become carbon. So what will happen is the sun's core will start to shrink, trying to make the carbon hotter and hotter. And as the core shrinks, of course, it gets hotter. And the envelope also begins to expand. Now, it's at this point where the sun is going to experience something quite dramatic. And let's start off with this animation. What's going to happen is the sun is going to begin to pulsate its outer envelope. Now, pulsation means, in this case, growing bigger and smaller and bigger and smaller over and over and over again. That's what pulsation means. Here is a series of photographs taken of a star that is currently experiencing this point of its evolutionary sequence. The star is called Chi Cygni, and these are pictures taken with a very, very sophisticated telescope that can actually reveal the surface of the star. So you're actually seeing the surface of the star. Now notice the dates that go by. May of 05, October of 05, March of 06, and then May of 06, and then it repeats. Now, for a sense of scale, notice this is the size of the Earth's orbit, so this is 1 astronomical unit right here. Notice this star is growing bigger, and then smaller, and then bigger, and then smaller. So this star is literally pulsating its outer envelope, growing steadily larger over a period of months, and then growing smaller over a period of months. And then it repeats, bigger and smaller and bigger and smaller. Now, astronomers are not really sure why this is. There are a few beliefs, or there are a few theories as to why a star could do something like this, why a star would pulsate its outer envelope, growing smaller and then bigger and then smaller. One of the ideas is that when a star starts to puff out its outer envelope, the movement of the envelope outward creates momentum. Think of it as you give something a shove, it keeps on going. And so the envelope pulsates outward, and the momentum makes it grow a little bit bigger than it was supposed to be. And then, of course, that'll slow down, and gravity takes over and tries to pull it back in to correct that. But what'll happen is when the envelope pulsates outward, and then, of course, gravity kicks in and tries to take over, the star gets pulled back inward. Now, when you pull the star inward, you shrink its volume, and you have to, of course, that means raise the temperature. The volume of a gas that shrinks becomes hotter. So as the star shrinks down, it basically overcorrects, getting hotter than it was supposed to get. And then so the increasing temperature of the envelope is then now going to force the envelope to expand. When you heat a gas, it expands. So this overcorrection makes it hotter than it's supposed to be, which then now makes it expand, but then the momentum overshoots the size it's supposed to be. Then gravity kicks in and starts to pull it back inward. So what we have is essentially a correction made by gravity that is trying to happen, but it's basically failing every time. So you have an overshooting of the size, followed by an overcorrection, followed by an overshooting of the size, followed by an overcorrection. So essentially you get this instability where the star is trying to correct the fact that it's suffering through these two issues. And so for a period of many thousands of years, the star is going to pulsate back and forth, growing and shrinking and growing and shrinking. Now, there's a price to be paid for this pulsation. Let me show you how this is going to affect the star. Every single time the star grows slightly bigger and then shrinks back in on itself, what's going to happen is this red giant star is going to puff off a little bit of its outer envelope. And then it's going to shrink back in and then grow a little bit bigger and push off a little more of its envelope. And then it's going to shrink back in and then turn around and grow bigger. So this pulsation outward, inward, very steadily for thousands of years, ultimately causes the star to push off its entire envelope. And this is a photograph of a star, an intermediate mass star, that has ejected or pushed off its entire envelope. And this cloud, although it looks like it's not doing anything in this picture, this cloud is steadily getting larger and larger and larger as this star has pushed off its outer envelope. Now, this type of a cloud has a name, and I'll warn you, the name is not necessarily accurate because of a misunderstanding from a few centuries ago. These clouds are called planetary nebulae, that's the plural. This is a planetary nebula. And you'll notice that it says has nothing to do with planets. And the reason why they're called this is because a few centuries ago, when they were first seen through telescopes, it was believed that people were seeing planets, or particularly the formation of planets. In reality, this is a star that has ejected its outer envelope. And about 40% of the star's total mass gets pushed off into space. Now, what you'll notice is at the very center is this little tiny white dot. That is the core of the star that has pushed off its outer envelope. And we call that a white dwarf. So the remnant core is a white dwarf. The envelope that gets pushed off into space is called a planetary nebula. Now, in our next video, we're going to talk more about white dwarf stars, these remnant cores, and what we can learn from them. And then, of course, we'll start to talk about what high mass stars do when they die. We're running short on time, so I hope you'll join me then.